Hi, a very warm welcome to Ushendra's engineering tutorials. A topic from control systems which cannot be neglected. University exam point of view. A topic from time domain analysis. Step response of a underdamped system, second order system. So under what classification? The second order systems falls under underdamped here for zeta value, for the damping factor zeta value being greater than 0, less than 1, this value of damping factor makes the system to fall under the classification underdamped, isn't it? And here is a transfer function. We have a C of s by R of s. Output by input is equal to omega n square, and this one here we have the frequency, natural frequency, and the damping factor which we are talking about, and which decides the behavior of the system. And denominator equal to 0, that gives the characteristic equation, the pole location of the system. Here, comparing this with the standard quadratic expression, what we have is we have seen in our previous grades from the beginning. We need to compare this with ax square plus bx plus c equal to 0, and from this we need to extract what is a. A will be 1 in this case, and this is our b here, this is our b, and this is our c, making no mistake. So plugging in those values like quadratic expression, two roots, that will be s1 comma s2 for that expression which we are talking about. So minus b plus or minus under root b square minus 4ac by 2a, guys. So going ahead, plugging in the values, right? So b, what's our b? It's 2 zeta omega n. So that will be minus of 2 zeta omega n plus or minus under root p square, again this one b square, isn't it? So that square, it will be 4 straight away, 4 zeta square omega n square minus what's our 4ac? It's a 4, a is 1 and c is straight away omega n square, and the root is for the entire expression upon the denominator is for entire expression. 2, a is 1, so that's our resultant, the roots. So still, which will be equal to what? It's a 2 as it is, minus 2 zeta omega n plus or minus, guys, are taking out from this one this, and this taking out 4 omega n square can be taken out as common from this and this, and also taking that term out of the root, under root, that will be twice of omega n. Square gets cancelled with that root, so it will be, so what is left over there? It's a zeta square minus 1, 4 omega n square came out, right? So in this case, with this transition, this gets cancelled here, these values gets cancelled. And guys, if this is the case, we have an imaginary over here, isn't it? So these are the roots of the second order underdamped system, and so this will be here, like going ahead, taking out it's a no more denominator over here, minus zeta omega n plus or minus, guys, taking out minus 1 here itself. So took out picked out minus 1 from here, that will be having 1, positive 1, and negative 1 is taken out from here, it will be negative of zeta square, right? Omega n will be as it is, no change, we can do it's as it is. And so this gives us this under root minus 1, that gives us minus zeta omega n plus or minus omega n as it is, right, as it is. And here we have the term, imaginary term j for this one, and so we going ahead, it will be under root 1 minus zeta square. Guys, these are the roots, and so with this values, the roots of the underdamped second order system will be lying in the second and third quadrant. Check that. And here this will be roots 1 and 1, the two roots of the second order system, right? And here, even more simplified version, this will be minus zeta omega n plus or minus j times, guys, this entire term is written as omega d. It's a natural frequency. When multiplied with the damping ratio, that becomes damped frequency of oscillations. It's damped frequency of oscillations, and that is denoted with this one. So if omega d, here we need that one, omega d is omega n under root 1 minus zeta square. And what will be omega d square? We need all these. Omega d square will be equal to omega n square into 1 minus zeta square. Guys, we need all these to plug in somewhere for simplifications, right? So in that case, so that happens with all the discussion. Now coming back to the transfer function, these are output and these are input, and we are talking about the response of a underdamped second order system subjected to step input. Now which gives us C of s. The output C of s will be equal to R of s to RHS. That will give us, it's a input, so we are talking about step input. The Laplace transform of the step input will be 1 upon s, so the transformation will be omega n square by s for the 1 by s for the step input R of step input, s square plus 2 zeta omega n s plus omega n square. So this is the transformation. And hold on, we have to evaluate the response of a second order system, underdamped second order system, and that should be in time domain, right? It's in Laplace domain, making use of partial fractions, etc. going on, and simplifying to a standard Laplace transform pair. The inverse Laplace transform gives us the response of the second order system when subjected to step input, underdamped second order system. That's the procedure over here. So in that case, making use of this could be split into, it's a partial fractions, and we have a quadratic expression over here, and that will be, it takes the form a by s for this one, the first term, plus bs plus c upon this one, the quadratic expression as it is. The procedure to write the partial fractions, x square plus 2 zeta omega n into s plus omega n square, isn't it? Now how to evaluate the value for, evaluating the values of a, b, c, plugging in, we'll go back to this one, what this says, right? So how to evaluate the value of a over here? It's going back to this very, picking this very expression. A will be this one, omega n square by s into s square plus 2 zeta omega n into s plus omega n square, multiplying with the a residue, that's s, and subjecting s is equal to 0. This is a procedure to evaluate for a, and in that case, this s here, this s over here and this s over here gets cancelled. Plugging in the value of s is equal to 0 over here, this becomes 0 here, this becomes 0, and even this entire term becomes 0 because we have s over here, right? In that case, only omega n square in the numerator and omega n square in the denominator is left over. So we'll be having omega n square by omega n square, and this is the value of our a. And so plugging in the value of a over here will help us to evaluate the values of b and c in a single shot. That's how to write that one here. Our c of s, which is equal to omega n square by s into s square plus 2 zeta omega n into s plus omega n square. We have a, we have evaluated a, so that will be straight away 1 upon s plus bs, sorry, a bigger one, bs plus c by s square plus 2 zeta omega n into s plus omega n square. Now this will help us to evaluate the way of values of b and c in a single shot. Plugging in the value of a in the expression, the partial fraction which we have obtained right now, it will be 1 upon s plus bs plus c. B value and c value aren't evaluated yet. S square plus 2 zeta omega n into s plus omega n square, isn't it, as it is? So there is a separation, don't mind. And this one, simplifying for this one, what it is, this into this, it will be s into s square plus 2 zeta omega n into s plus omega n square, right? And this should be cross multiplied, isn't it? So this term repeats again for 1, so that's s square plus 2 zeta omega n into s plus omega n square plus this into this. We are done with this one. This into this. That gives us b s square plus c s, right? On this side we have, which is equal to omega n square by s into s square plus 2 zeta omega n into s plus omega n square, right? So equating the two ratios on either side, LHS and RHS, denominators are same, right? That gets cancelled. And equating the like terms on either side, yeah, 1 second, there is a small simplification over here. Denominators got cancelled. Picking out s square as common from this, so that will give us 1, and from this that will leave us b plus b over here, plus going ahead picking out s, that will give us what, 2 zeta omega n from this term, 2 zeta omega n from here, and the same s which is from here, that gives us plus c, isn't it? Plus what are we left with? It's a omega n square is left over, right? So which is equal to omega n square on this side. So this will be equal to 0, this will be equal to 0 because we don't have s square and s term on this side, right? So omega n square, omega n square, that's right, no problem with that one. So what it is, s square into 1 plus b will be equal to 0, that will be 1 plus b will be equal to 0, and our b which we are searching for will be equal to minus 1, right? And on the other hand, from here straight away c will be equal to minus of 2 zeta omega n. Guys, plugging in these values over here will help us to reach to that expression which we are trying for. So considering that again, c of s will be, rewriting over here please, c of s will be 1 upon s plus b is evaluated to be minus 1, so that will be minus of s, and c is minus of 2 zeta omega n. Guys, can this be written as minus of zeta omega n minus of zeta omega n? Of course, adding that we'll have this one, right? And what to do with the denominator? It's a s square plus, yeah, there is a small change over here also. For some simplification, we need to bring to it a compact form, valid Laplace transform pair. So this one, it will be s square plus 2 zeta omega n into s. Guys, can we do this? It's a positive zeta square omega n square, yeah, negative zeta square omega n square. Adding these two, I mean adding and subtracting doesn't matter, plus omega n square. Can we do this? Of course. And how can we close this here? In that case, how can we close this from this point to this point? Check carefully. It's a c of s is equal to 1 upon s as it is, plus it's a minus of s minus zeta omega n by here omega n. It's a s plus zeta omega n whole square, a plus b, it's in the form a plus b whole square. So s plus zeta omega n whole square, and one more transition over here, right? Taking out omega n square as common from this and this, what will that lead to? Omega n square is taken out as common from here, so that will be 1 over here, and negative is left over here, negative, this has come out, so it will be zeta square, right? So for this one, and for that it will be minus of zeta omega n as it is, and continuing this one, this same denominator comes for that even, right? S plus zeta omega n whole square plus omega n square into 1 minus zeta square, right? And guys, one more small change over here. Taking out this negative as common from both the terms here, this negative appears over here, and this will be no more negative, this will be positive, right? This one. Can you see this? Guys, rewriting this expression over here, I have taken a halt over here. It's as it is, 1 upon s as it is minus this as it is. But there is a small, this could be written as, here from this one, it's omega d square, omega d square. From here, omega n square, from here, this could be written as. And so in that case, even the denominator of this term also will be the same, right? So that will be, it's s plus zeta omega n whole square plus omega d square. It's as it is. And will there be any problem if you write this one like omega d upon omega d? Is there any problem? No, because that get cancelled, and writing that zeta omega n as it is. Here this has come as it is. I've just multiplied the numerator and denominator with omega d, closing this one. It's this, right? So in that case, this will be as it is, 1 upon s will be as it is, minus s plus zeta omega n by s plus zeta omega n whole square plus omega d square as it is, minus of, guys, here even this one same, s plus zeta omega n whole square plus omega d square is also as it is. A small changes over here. It's omega d is left over here, and zeta omega n. Can this omega d be written with, substituted with this one? Of course. So in that case, it's omega n into under root 1 minus zeta square. Guys, here this omega d separated, and something gets cancelled over here. This and this gets cancelled, right? So that's it. Now this is in a standard form here. Now this ratio and this ratio, this one, this ratio is a valid transformation pair, Laplace transform pair. We have you can find the proof for, what's that, Laplace transform of e raised to minus at cos bt will be equal to s plus a by s plus a whole square plus b square. In the same way, Laplace transform of e raised to minus at sine bt will be equal to b by s plus a whole square plus b square. Guys, you can find the proof in the link which is provided in the description box. It's already done, right? Please find the link in the description box. Now this is our, here it's very clear, s plus a, right? This is our a, zeta omega n being our a, and omega d being our b. This is our b. Comparing that, these two. And here once again, this is our b, here omega d b, it's a again, this is our a and this is our b. So this could be reduced to its, now considering the inverse Laplace transform, that will give us the transformation. It's an S domain, the inverse Laplace transform will be in t, c of t will be equal to, it's a 1 upon s, the Laplace transform, the inverse will be equal to 1, it will be back to the step function 1, minus, even this can be, you can see the proof, Laplace transform of unit step function is 1 upon s, so the inverse will go back to 1. And here this could be reduced to minus of e raised to minus, what's our a, minus zeta omega n and t, and multiplied with cos, what's our b, it's a omega dt, right? This is our b. And going ahead for this one, it's nothing to do with this one, zeta upon under root 1 minus zeta square as it is from this term. Now this will be e raised to minus, what's our a, it's minus, zeta omega n is our a into t sine, what's our b, it's a omega dt. Guys, that's the expression which we are searching for, which will be equal to 1 as it is minus, guys, something can be taken out as, yeah, here, not yet, even this is taken out as common, that should be mentioned. Taking out negative as common from this one and this one, so that's negative came out here, this negative has come out. Even something else can be taken out as common, e raised to minus of zeta omega nt as common from here, and here something else also can be taken out. It's under root 1 minus zeta square could be taken out. So if this is the terms which are taken out, so what will be left over here? Will be here, it will be cos omega dt into this one under root 1 minus zeta square, because we took out this one as common from both the terms, right? So it will be we have taken this negative, so that will be positive, and sine omega dt here, now t multiplied with zeta. This is the transformation. Now guys, what if we can construct a triangle with the values of zeta here? What if we have a triangle like this and having a theta over here, and this side with 1 minus zeta square and zeta over here? Can that be okay for a right angle triangle? Of course, we have this square plus this square will be equal to 1. Now this one will be, and from here what will be our sine theta? Sine theta will be equal to opposite by hypotenuse, right? So that will be under root 1 minus zeta square. And what will be our cos theta? It's a cos theta will be equal to adjacent upon hypotenuse, so that will be simply zeta. Guys, these are the values. In the sense, under root 1 minus zeta square will be equal to sine theta, can be plugged in with, and zeta that can be reversed. So what will be tan theta here? Tan theta will be equal to what? Opposite by adjacent, right? So that will give us under root 1 minus zeta square by zeta. So this is the values, important values. So now if this is the case, making use of this one, this will be sine theta and this will be cos theta. So make a note please. So the expression will be c of t will be 1 minus e raised to minus zeta omega n into t upon under root 1 minus zeta square, and inside the bracket what we have is cos. Guys, it's a positive, I'll just flip it, that doesn't matter, that won't change the characteristic. It's a sine omega dt plus, this zeta which is cos theta into cos theta plus over here, and this is also plus cos omega dt into under root 1 minus zeta square, that will be sine theta from here. So it's sine theta, isn't it? Now can you see this? Sine A cos B cos A sine B, that could be reduced to is equal to 1 minus e raised to minus zeta omega n t under root 1 minus zeta square as it is. Now this could be reduced to sine omega dt plus, omega d is the suffix over here, don't mind, dt plus theta. Our final expression is equal to c of t, the response of a c of t, the response of a underdamped second order system subjected to step input. The discussion will be incomplete if we don't show the characteristic, the response. So drawing that also, let's finish it away. We have c of t on the vertical axis and for different values of t tending to infinity. So what's the input in this case? It's a step input, unit step input, so it will be 1. And the response starts commencing from t equal to 0. It starts commencing from t equal to 0 over here. Hold on. So why t equal to 0? For a beginner, he may be confused. How can you say that it's t equal to 0? It starts commencing from t equal to 0. Here, hold on. It's a t equal to 0. Come back to the expression t equal to 0. When t equal to 0, this will be 0 and we'll be left with sine theta. And this sine theta and this under root 1 minus zeta square are equal from the triangle, and this gets cancelled. Is that clear? And we are left with this one, right? E raised to t over here, so e raised to 0, that will be 1, and so coming back 1 minus 1, that will be 0. So this is the proof. It starts from t equal to 0, and these intermediate values cannot be proved for the time being. It gets diminishes at t as t tends to infinity and reaches the final value. And what is that proof? At t equal to infinity, t tending to infinity, this matches the output matches the input. Here, come back to this one. Here we have e raised to, forget about this one, e raised to minus, this entire term will become infinity. E raised to negative infinity, that will be 0, and so the entire expression will be equal to 0, we'll be left with 1, that's we are left with 1. Right? The response of a second order underdamped system subjected to step input. Hope you understood, hope you find it useful. Please support me with your valuable share and a subscription. Thank you for watching.